Good day everyone. Welcome to today's presentation on counting all triplets with a given sum in a sorted array. In this session, we will explore an efficient solution using a combination of two-pointer technique and duplicate handling, optimizing the approach to solve the problem effectively. Our problem statement involves a sorted array where we are tasked with finding all the triplets that sum up to a specified target. The challenge is to count all unique triplets that satisfy the equation ARRI plus ARRJ plus ARRK equals to target, where j is greater than I but less than k. As we look at some examples, we will understand how the solution unfolds. For instance, given an array containing the elements -3, -1, -1, 0, 1, 2, and a target of -2, the solution yields 4 valid triplets. To break the problem down further, we have two key components, the input, the expected output. The input consists of a sorted array and a target value, while the output is simply the count of all valid triplets that sum up to that target. Understanding this foundational structure will guide us through the solution. We start with the brute force method, which involves checking all possible triplets in the array using three nested loops. While simple to understand, this approach has a time complexity of big O of n cube, which is inefficient for larger arrays due to the high number of computations involved. Thus, we seek a better solution. The optimized solution utilizes the two-pointer technique. We iterate through the array, selecting one element as the first element of the triplet. We then use two pointers, one starting from the next element and the other from the end of the array. By adjusting these pointers based on the sum of the elements, we can efficiently find valid triplets. This reduces the time complexity significantly to big O of n squared. An important consideration in our solution is handling duplicates. When two elements at the left and right pointers are the same, we need to calculate how many valid triplets can be formed by choosing different pairs of these elements. For such cases, we use combination to calculate the number of ways to select these elements. When the elements are different, the number of valid triplets is simply the product of the count of both elements. Let's look at the core of our implementation. Here we define a class solution with a function countTriplets, which takes in the sorted array and the output value. We iterate through each element in the array and apply the two-pointer technique. If the sum of the triplet is less than the target, we move the left pointer to the right, and if it's greater, we move the right pointer to the left. As we continue, we calculate the sum of the elements at the pointers. If the sum matches the target, we then count how many occurrences of the elements at the left and right pointers are present. This helps us handle duplicate values efficiently by adjusting the left and right pointers accordingly. To count the duplicates, we increment the count of the left and right elements, moving the pointers to find other occurrences. If the elements at the left and right pointers are the same, we calculate the number of ways to choose two elements from the available occurrences. Otherwise, we simply multiply the counts of the elements at the two pointers to find the number of valid triplets. Let's walk through an example. For the input array -3, -1, -1, 0, 1, 2 and a target value of -2, we start with the first element -3. Using the two-pointer approach, we find four valid triplets -3, 0, 1, minus 3 minus 1 2, minus 3 minus 1 2, and minus 1 minus 1 0. This illustrates how the two-pointer approach efficiently finds the triplets without unnecessary comparisons. Let's look at another example. With the input array minus 2, 0, 1, 1, 5, and a target of 1, no valid triplets are found. This highlights how the approach handles different cases, ensuring that only valid triplets are counted. Now let's analyze the time complexity. The brute force approach with its three nested loops runs in big O of n cube time. However, by using the two-pointer technique, we reduce the complexity to big O of n squared, as we only need to traverse the array once while adjusting the pointers. The space complexity remains big O of 1 since we only use a constant amount of extra space. In conclusion, the brute force approach, while simple, becomes inefficient for larger arrays. The optimized two-pointer technique significantly reduces the time complexity, making the solution scalable. Handling duplicates properly ensures that we count valid triplets accurately. This approach is an excellent example of how thoughtful optimization can drastically improve the efficiency of an algorithm. Thank you for your attention. This concludes the presentation. I would be happy to take any questions or engage in a discussion about the topic. Please feel free to ask.